Math 2414, surface area of revolution, video 4. Surface area, example 2. If you hung around until the very end of the previous video, I hope my slowly but more maniacally laughter didn't scare you. I didn't mean to imply that these problems are going to drive you crazy, but some of them will. So hope your integration skills are honed. Find the lateral surface area of the solid obtained by revolving the graph of y equals x squared from 1, 1 to 2, 4 around the y-axis. Now, what's the biggest difference between this problem and the previous one? If you said it's the ordered pairs, not really. I just gave you the actual coordinates of the beginning and the ends of the graph as opposed to just the range of x values. If you said around the y-axis instead of the x-axis, bingo. All right, let's sketch this real quick, which is not really that difficult to do. It's just y equals x squared, which is your standard parabola. But we're going from the point 1, 1 to the point 2, 4, which is about there. So it's not much of this graph that we're going to spin. We're going to spin it around the x-axis. No, we're not. We're going to spin it around the y-axis. Okay. So how are we going to do this? Well, when we rotate around the y-axis, we're going to set up the integral of 2 pi x ds. So let's start there. Integral 2 pi x ds. And again, notice I didn't put the limits of integration because I have not yet decided whether I'm going to do this as a dx integral or a dy integral. That decision is driven by whether your equation is a function of x or a function of y. Since this says y equals x squared, y is a function of x, so we can call this f of x, which means we're going to do a dx integral. So, 2 pi x dx, and when we unpackage the ds, it will be 1 plus the square of the derivative of f of x. So unlike the previous example where we went around the x-axis, we don't have f of x here, we just have x. That's the part that's going to get you if you're not careful. All right, so this one's going to be pretty easy to set up because this function is easy to differentiate without much hoopla. If you don't know the derivative of x squared, shame on you. Oh, it's a dx integral, so now we can put our limits of integration. It's going from x equals 1 to x equals 2. 2 pi x square root of 1 plus the square of the derivative, but the derivative of the function is just 2x. All right, so let's square this and figure out where to go next. Integral from 1 to 2 of 2 pi x. Square root of 1 plus 2 squared is 4, x squared is x squared. And now we have to make a decision on how to integrate this. I want to remind you that we have quite a few integration techniques. We have just flat out rules, this isn't one of them. We have substitution, we have integration by parts, we have trig integrals, we have trig substitution, and we have partial fractions. But you should always ask yourself, can I just flat out do a substitution? And the answer in this case is yes. The thing about this that says substitution is that the clunky part under the square root, if we took its derivative, it would just be 8x, and we have an x over here that we can trick out into an 8x to build our du package. So we are going to do a substitution. We're going to let u equal 1 plus 4x squared. Then we have du is equal to 8x dx, so we'll dress up the du package in just a second. And since this is a definite integral, we have the option of changing the limits of integration. Why don't we go ahead and do that? The lower limit of integration, let's do the upper limit first. The upper limit of integration is x equals 2, but this implies that u is equal to 1 plus 4 times 2 squared. Well, 2 squared is 4, times 4 is 16, plus 1 is 17. And the lower limit of x equals 1 implies that u is equal to 1 plus 4 times 1 squared. 1 squared is 1, times 4 is 4, plus another 1 is 5. So in a moment, we're about to change this to a u integral, including the limits of integration. But first, let's stress up the du. So we'll leave the limits of integration alone just for a second. I'm going to take the 2 and the pi out because they're constant factors and they're kind of in the way. And I'm going to move the x over with the dx. I don't have to physically make these changes to the integrand. I'm just doing it to make the substitution move a little more transparent. So just shuffled some things around. I need du to have an 8x dx. I don't currently have an 8, so I can multiply by an 8 as long as I balance it with its reciprocal on the outside. And now I'm ready to make the substitution. The coefficient in front is pi over 4. The limits of integration change from 1 to 2 to 5 to 17. The radicand, the part under the square root, becomes the u, but it's a square root, so let's go ahead and rewrite it as a 1/2 power. And all this over here becomes du collectively. So as a calculus 1 problem, this just suddenly got easy. That's just the power rule. Let's move it over here. So continuing, pi over 4. The antiderivative of u to the 1/2, I would add 1 to the power to get u to the 3/2, then multiply by its reciprocal, which is 2/3, and this is being evaluated from 5 to 17. Well, let's clean up this product of fractions over here. I can reduce by 2. This 2 goes into this 4 twice. That will leave 2 times 3 on the bottom, which is 6, which is parked underneath a pi. And we're evaluating u to the 3/2 from 5 to 17. So we would get 17 to the 3/2 minus 5 to the 3/2. Should we do anything with that? Well, let me tell you what I don't want you to do. And I've written this on a few people's homeworks. Didn't take off points, just a little FYI. I don't want decimals. From a theoretical perspective, anytime you put something like this into a calculator and it comes out to be an irrational number, a long, non-repeating, never-ending decimal, whatever you write down is not the exact answer. It's close, but it's not exact. Theoretically, you want to maintain as much precision as possible, meaning stay away from decimals. The only time you should consider decimals is when A, the problem starts with decimals, this one didn't, or B, you're being asked to estimate a value or measure something to a nearest number of decimals, in which case you would do that. In other words, in terms of applications, yeah. If I needed to measure how long something was and this was the answer, I'd put that in a calculator, get a decimal approximation and use that. But in terms of theoretical math, don't resort to decimals unless you're told to resort to decimals or decimals are in the beginning of the problem. So what can we do with this? Well, we could rewrite it as the cube root of, the square root of 17 cubed and the square root of 5 cubed. But in terms of simplifying it from an arithmetic perspective, from a numerical perspective, I think I've shown this trick before, but there's a trick to simplifying something like 17 to the 3/2, and specifically a number raised to an improper fraction. The trick is to rewrite the improper fraction as a mixed number, in this case 17 to the 3/2 is the same as 17 to the 1/2 power. And then unadd the whole number with the fraction part by splitting into the product of 2 powers of 17. All I did is the adding exponent rules in reverse. These 17 start to look like pies. 17 to the first power is 17, and 17 to the 1/2 power is the square root of 17. And I could do the same thing for the 5. So if I did all that, I'd get pi over 6 times 17 times the square root of 17 minus 5 times the square root of 5, which I think is the best answer you can get theoretically without the assistance of a calculator. If you wanted a decimal approximation, then you would get out a calculator. So in retrospect, this one really wasn't that bad. The setup wasn't too bad because the function was easy to differentiate. And even the integral wasn't that unreasonable. It was just a substitution. I think the weirdest part was actually simplifying the answer. Okay, so that one wasn't too bad. But I do want to kind of leave you with a follow-up, which is going to lead into the next video. We did this as a dx function. A dx integral, because our equation was given as a function of x, y equals x squared. But this graph is not just a function of x because it passes the vertical line test, it's also a function of y because it passes the horizontal line test. Which means I could think of this as a function of y. And if I did that, how would it change the problem, and will it change the answer? Well, it shouldn't change the answer because it's the same shape, it just had the same surface area. So in the next video, we're going to see what would happen if we actually viewed this graph as a function of y instead of a function of x.